what we do in Calculus 1 is integrating things of the form x to the n dx. Okay, now remember, integrating x to a power dx, what we're doing with integration is we're reversing the derivative rules, right? So if we were taking the derivative of x to the n, we'd pull the n out front to multiply and then subtract 1 from the exponent. So when we are integrating, we do the opposite. So rather than subtracting 1 from the exponent, we add 1 to the exponent, except I just integrated that. And then rather than multiplying by the original exponent, we divide by the new exponent, right? Now, the only exponent for which that rule doesn't work is n equals -1. If we were integrating 1 over x dx, or the integral of x to the -1 dx, can anyone remember whose derivative is 1x? You're going, oh man, we're questions ready today. It's kind of different. And it starts with a natural
log.
Yeah, it ends with a log. Okay, so
Yeah,
the integral of x to the -1 dx, remember, is the natural log of absolute x plus c. And so when the exponent to which your variable is raised is -1, you get a natural log in your answer. Okay, so for this guy, what do you think we would do first? Well, our integration rules deal with exponents, not radicals. So the first thing I would do to integrate this is rewrite this in radical form. The square root of x is x to the 1/2. Since this first square root was in the denominator, it's going to be an x to the -1/2. And then we have plus 5 x to the 1/2 dx. Now, going back to your Cal 1 techniques, remember the integral of a sum of functions, you just integrate each function and add them together. Or the integral of a sum or difference is the sum or difference of the integrals. So I'm going to integrate this piece. Since it's a 5 times, the multiple of 5 is going to be a freebie, so it's going to come along. And then we're going to integrate x to the -1/2 dx. To do that, we're going to add 1 to the exponent. If you add -1/2 plus 1, you get +1/2 and divide by the new exponent. And then we do the same thing for the second part. If you add 1 to this exponent, 1/2 plus 1 is 3/2 and divide by the new exponent. And then instead of putting a plus C1 and plus C2, we usually just put one big plus C arbitrary constant at the end. Now let's go ahead and simplify. Dividing by 1/2 is the same thing as multiplying by 2 over 1, right? Dividing by a fraction is multiplying by the reciprocal. So we're going to have 5 times 2x to the 1/2 plus 5 times 2/3 x to the 3/2 plus c, or we get 10 x to the 1/2 plus 10/3 x to the 3/2 plus c. Any questions about that part so far? Are y'all still with me?
Yeah.
Oh, thank goodness. Yeah. I was like, I had total silence. And I was like, okay, that was just, it was just so very silent that I thought, oh, I may have lost audio.
No.
Okay. Now, one thing just to be upfront with you, usually I skip straight from here to here. Rather than dividing by the new exponent, I think of that as multiplying by the reciprocal. of the new exponent. So I don't go to this step. I go ahead and put it out front as the reciprocal of the exponent most of the time. Just saves that one step. All right, so what about this one? Well, we don't have an integral formula on that sheet of, what was it, 18 or 19 things that I sent you that deals with the product of integrals, or the integral of a product, unless it's like trig functions like secant tangent or cosecant cotangent, something like that. So one option here would be to just multiply this out first and integrate term by term. So we would get 4x times 11x squared is 44x cubed, minus 4x times 5x is 20x squared dx. Now I'm going to integrate term by term. So I will have 44 times the integral of x to the third. Remember, we're going to add one to the exponent and divide by the new exponent. So I will have x to the fourth times 1/4 minus 20 times x cubed times 1/3. And then plus c. Simplifying, 44 times 1/4, I believe, is 11. And then we'll have 20 thirds x to the third plus c. Now, one thing you can keep in mind is that you can check yourselves. Remember, if you just take the derivative of your answer, you should get something that is equivalent to the original integrand. Okay. Now, any questions at this point? I'll try to pause long enough for you to write those down. Go ahead. All right. And I will still, at about 1 o'clock, we'll probably take a little quick break so you can get you a cup of coffee or whatever. And we usually take about a 5-minute break in a 2-hour class. All right, example number 3. We have the integral of 4x to the fourth plus 4x squared divided by x. So once again, look at that list of things we know how to integrate, those 18 or 19 forms. And I go, that doesn't look like anything that's on there. I don't have any that have an x in the top and in the bottom. So one of the keys to being a good integrator is to A, know all those basic forms, and B, be able to rewrite your original integrand until it looks like something we know how to integrate. One of the kind of algebraic tricks, if you will, to rewriting it when there's a single term in the denominator is to break that fraction apart and simplify each part. Remember, you can break a fraction apart across addition or subtraction in the numerator. So this fraction is the same thing as 4x to the fourth over x plus 4x to the second over x dx. So it could just be rewritten that way. And what's nice about it in this form is now I can cancel out an x. So this would be the integral of 4x to the third plus 4x. Now, I talked about it like breaking the fraction apart. You could think about it as bringing this x up as x to the -1 and multiplying it through. The result is the same. But the point is we had to integrate, or to be able to integrate, we had to rewrite first. And now we're going to just integrate term by term. So we would have 4 times the integral of x to the third would be x to the fourth times 1/4 plus 4 times the integral of x, which is x to the first, would be x squared times 1/2. After simplification, we will get x to the fourth plus 2x squared plus c. So those have all been very similar in nature as far as the way we dealt with the integration part, but the second two examples, we had to do some rewriting first. So always keep in mind when you're doing integration, if it doesn't match something on our list of things that we know how to integrate, we're going to rewrite the integral until it does. Okay. All right, trig functions, everybody's favorite.
Oh my God.
So we have -6 times. Which trig function do we take the derivative of and get secant x tangent x? Whose derivative is secant tangent? I feel like I should have Jeopardy music.
Almost got it. Give me just a second.
Oh, you're fine.
I was thinking secant squared, but I'm not here today, so.
You're close though. It's not squared. It's just
secant.
Excellent. The derivative of secant x is secant x tangent x. So the integral of secant x tangent x is secant x. Okay. And then -7 times whose derivative is secant squared?
Is it 10?
Yes. So we've got 7 tangent x
It's on the sheet, guys.
plus c. So just a reminder, if you take the derivative of sine x, you get cosine x. So the integral of cosine x dx is sine x. If you take the derivative of cosine x, you get negative sine x. So the integral of sine x dx is negative cosine x. Better not forget my plus c there. Okay. The derivative of tangent x is secant squared x, and the integral of secant squared x dx is tangent x plus c. Derivative of secant is secant tangent. So we're going to reverse it with integration and would get the integral of secant x tangent x dx would be secant x. And then I've got cotangent x. The derivative of cotangent x is negative cosecant squared x, which means that the integral of cosecant squared x dx is negative cotangent x. And then the last one that we haven't done is cosecant x, I believe.
Yep.
Derivative of cosecant is negative cosecant x cotangent x. So the integral negative cosecant x plus c. And notice that 6 trig functions are combinations of trig functions that we know what the integrals of are just because they're the actual derivatives of another trig function. But I don't even know what the integral of tangent is based on those basic ones. Now it is on your list and we'll derive it here in a few minutes, but these guys, if you know your derivative rules, you're just reversing them. Okay. All right. What about this guy? Now remember, could I rewrite this as 1 over 15 times the integral of 1 over y dy? Is that fair to do? Oh yeah, you can factor constants out in front of integrals just like you can in front of derivatives. And all right, I think it was Timmy earlier. What's the integral of 1 over x or 1 over y? It has a what in front of it?
Natural log.
Natural log. So this would be the natural log of the absolute value of y plus c.
Nice.
All right. How are we doing so far?
Good.
If you are feeling a little overwhelmed, going, okay, I don't remember all, okay, trust me, you're not alone. They will come back to you. You just have to practice with them and make the effort to memorize them, because if you will memorize those basic rules, the rest of it will be much, much easier than if you don't memorize them. Okay. All right. So what about this guy? Well, I'm going to go ahead and factor out the constants that I can, and hopefully that will help you guys just a little bit. That would be 8 over 25 times z squared plus 1 dz. So I could factor an 8 over 25 out front, and I would have 1 over z squared plus 1 dz left inside the integral. Does anybody remember whose derivative is 1 over z squared plus 1? And I know this is a big ask because we didn't do a whole lot of these in 5.5.
I don't know why, but I'm thinking like it reminds me of arctan or something like that.
That is arctan. Yay! What's your name?
Avery.
You go, Avery. Okay, sorry, I can't see the chat or the list of people with their stuff on, their microphones on. That's excellent. This is the integral that is equal to arctangent of z. Excellent. So we would have 8 over 25 times the arctangent of z, or we might say 8 over 25 tan inverse of z plus c. Either one of those notations would be okay. Now, on your sheet, I believe I did the more generic version. We do have, so that you don't have to factor out the constants every single time, if you have something of the form du over u squared plus a squared, in general, that will be 1 over a times the arctan of u over a plus c. And it comes down to a variable expression squared and a constant squared. It's just sometimes this constant and this constant are different numbers. So just factoring it out front and getting a z squared plus 1 is kind of a painful process. But if you do it for an arbitrary setup like this, you end up with 1 over a arctan of u over a. These are the ones I particularly, recommend that you really make yourselves flashcards and try to memorize those, because it will save you a lot of time over the course of the semester. All right, if anybody is wanting to write that down, are you good? If you need me to not go to the next page yet, just type no in the chat. All right. Another thing that we do sometimes is we, instead of having an indefinite integral where we don't know the constant, sometimes we're given enough information so that we can evaluate what constant would make it work. Okay, so for example, let's say for the function f given below, we want to find the antiderivative of f that satisfies f of 1 equals 2. And so my function f, I'm going to say that f of x is going to be e to the x. Okay. very often when you see lowercase f and uppercase f, what we have is that the lowercase is the integrand and they use the uppercase to represent the antiderivative. So we want to find an antiderivative of f. So that means that an antiderivative f of lowercase f. So big F will be the integral of e to the x dx. Now, who remembers what the antiderivative of e to the x is?
E to the x?
Yay, e to the x. That was our favorite one because if you just wrote down the original problem, you got the answer right. Remember, the derivative of e to the x is e to the x, and therefore the integral of e to the x is also e to the x. So this would be e to the x plus c. Now, we want to find out of all these infinitely many possibilities, we want to find the one function, capital F, that satisfies the condition f of 1 equals 2. So if this is my capital F, then f of 1 would be e to the 1 plus c. And we want that to equal 2. So we're going to just solve for c using this statement. So c would be 2 minus e. So our capital F, whose antiderivative, who is the antiderivative of e to the x, would be e to the x plus 2 minus e. Is everybody okay so far?
Yep.
All right. I want you guys to try just a couple, okay? I want you to take just a couple minutes and try these two integrals. Now, normally if we were in like face-to-face class, I would just, have you comparing your answers with each other. That's a little bit harder to do here. So if you'll just take a couple minutes and try to work those out, then we'll compare answers I'll work them out and we'll compare. When you guys get to a point that you're ready to check them, just type an okay or something like that in the chat, if you will. And so I'll wait for at least a few people to say they're ready before I continue.
Hmm.
Okay. I may be jumping the gun, and if I'm going too fast, please let me know. Can you tell me how you rewrote this first one to integrate? 4 over x squared is the same thing as 4 times x to the what power?
Negative
The
2.
-1.
Excellent. It'd be -2 in this case. It's negative because the x was in the denominator, and it's 2 just because that's what it said. Okay. And then remember, the cube root of x squared, that's x to the 2/3 power. Just a reminder, the nth root of x to the n power in general, that's x to the n over m. The root that you're taking is the denominator of the fractional exponent, and the exponent of which x is raised is the numerator. So we have to write it as sums or differences of x to a power terms so that we can use our basic integrals here. So we would have 5 times the integral of x to the 3rd will be x to the 4th times 1/4. Add 1 to the exponent and divide by the new exponent. Then we'll have plus 4, the integral of x to the -2. Okay, now remember, the only time you have a natural log involved is when the original variable was raised to the -1 specifically. When it's a -2, you still just add 1 to the exponent. -2 plus 1 is -1, and multiply by the reciprocal of that new exponent. And the reciprocal of -1 is -1. Didn't quite leave myself enough room there. Okay, and then we have plus the integral of x to the 2/3 is x to the 2/3 plus 1 is 2/3 plus 3/3, which is 5/3, and then we multiply by the reciprocal of the new exponent, and then we have plus c. So we end up with 5/4 x to the 4th minus 4 over x, or 4x to the -1 if you prefer, plus 3/5 x to the 5/3 plus c. Everybody okay right there?
I have one question.
Yes.
So with the natural log, so if we were to take the integral again, would -4 over x then be natural log?
Yeah, if I took the integral of this term, we would have a -4 ln absolute x. Yes.
Okay, thank you.
You bet. All right. What about this guy? Anybody at all remember whose derivative is 1 over the square root of 1 minus x squared?
Arcsin.
Yay! Arc sine x. So we've got arc sine x plus c. And I know that, did everybody in this class use this textbook for Calculus 1, or did you take Calculus 1 somewhere that doesn't use this textbook?
I took it somewhere else.
Okay. Did you do derivatives and integrals of inverse trig functions in your Cal 1 class?
Yeah, and we did part of Calc 2.
Okay, so we're good. It's just some books may not do the derivatives and integrals of inverse trig functions until later. But if you took Calculus 1 using that book, let me know, and I will point you guys in the right direction for where to find derivatives and integral forms for inverse trig functions in our book. Okay, so at this point, we are going to take a quick break. It's 12:51 we'll take 9 minutes today. So I'm going to leave, of course, the Zoom on, but feel free to get up and go get you a drink or just walk around for a few minutes, and we'll start back up with the second half of class at 1 p.m. Unless y'all don't want to stop. I figured everybody just needed a little bit of a break.
Nah, I secretly went to go get ice cream during some
Oh,
of
that sounds delightful.
it. I have to eat while learning, you know?
Well, it's just better. It's
Yeah.
just better. That's all there is to it. And when it's ice cream, I mean, what are you going to do?
All right. Just like, I feel so lazy right now, just laying in bed, just.
Laying in bed, going to class. It's all good.
Yeah.
Our lives have changed drastically in the past 5 months, haven't they?
Yeah. I would be going crazy though if I didn't have a job because I would not be able to be stuck in the house all day.
Oh, it's sad that I have discovered I really don't mind. But oh well. I hope I've got to check the people in chat and make sure none of them are ditching us. Okay, y'all, I'm watching to make sure you don't ditch us during break. You're going, I don't care. I know you don't, but it's okay.
When is our first quiz around?
When? Let me pull. Well, I say let me pull it up. Let's see if I can pull it up on. Holy moly, that was quick. Knock on wood. All right, so here's your calendar. Can you see it?
Yeah.
Okay, so you've got a Gradescope practice assignment due at 2 p.m. this Friday, and your first quiz will be due at 2 p.m. next Friday.
Oh, okay.
So what I'll typically do, and I'm sure we'll probably talk about this some more, is like what we do in class today, the My Math Lab assignments will be due at right before class starts on Wednesday. What we do on Wednesday, those assignments will be due right before class starts the next Monday, and so on and so forth. And you can still get into those homework assignments after the deadline passes and still work on them some more. But just to kind of keep you on track to be ready for the tests and stuff like that, that's, what we've got.
Gotcha.
All right, let me stop that share and share what else I wanted to.
For the homeworks, like I used this program for my last calculus class. Do we get multiple tries on it, or is it like graded? Yeah, like ours was just we got one try on our homework.
Well, even in one try, it gives you 3 tries, right?
Yeah.
You got to miss it 3 times before it blocks you. But I actually left it as infinitely many attempts right now. Particularly for Calculus 2, and I'm just going to admit this to y'all, it can be really frustrating to enter your answers because some of the answers are really long, and so it's kind of a hardship if you just have one shot at it. Though I get it, and it's a good idea to, but yeah, you've got more than one shot right now.
Yeah, sometimes it doesn't like the certain way you put it in. It'll be like, it's wrong, but you're like, no, it's right.
And sometimes you hit that extra space and you can't see it in there anywhere. Okay, it's just hard some days. And that's why, like on a lot of your quizzes and all of your exams, there won't even be a place for you to type in an answer in My Math Lab. You'll write it down. You'll show all your work and get your answer on paper, and you won't have to enter it in My Math Lab. You'll just take, scan in or take a picture of your supporting work, enter it into Gradescope, and I will just hand grade it.
Okay, gotcha.
All right, I'm going to get myself finished topping off my coffee, and I'll be right back and ready to start. All right. I said 1, so I guess I better wait, hadn't I? I should have given less time because I'm ready to go. Ready to start back. Oops. Could y'all hear me talking to my dog?
I didn't hear you, but I was going and getting a
Oh,
snack,
good, because
so.
I'm like, I realize okay, I admit it. I never baby talk to my children, but I baby talk to my dog all the time. That could be really embarrassing for me.
Don't worry, I do the same.
I'm like, okay, we never ever, it's so weird. I never did it for my kids because, okay, you don't want them to grow up talking like that. But yeah, the dog, I figure we're pretty safe with her. She's probably not going to repeat it, right? Maybe.
What kind of dog do you have?
I have an Australian Shepherd.
Oh, that's my favorite kind of dog. I have a golden retriever.
Oh, they're so sweet.
Yeah, he's amazing. He's just like a family dog all the time, man. It loves to like hang around people and like hates being alone.
Yeah, she doesn't know what to do with the fact that I have been home pretty much every day for 5 months. She's like, I don't know why you people are always here, but you're interrupting my nap. But anyway, but all right, so we're ready to get ready and get going on section 5.5. So our homework for today that will be due at the beginning of class next time is review problems from 4.9 and 5.5. So it's basic integration techniques like we're doing here. Now, are y'all seeing the piece of paper again?
Yeah.
Okay.
Yes.
So on this one, we've got a little bit more going on in section 5.5. So these guys don't exactly match the forms that we have in our list. And so if you'll remember, when they don't match to begin with, we just rewrite them until we do, or until they do. And so we use substitution. Sorry, didn't mean to mess with the camera there. Okay, so if I'm thinking this may be one of those of the form 1 over u du. Because I know how to integrate that. What do you think I should choose for you to do a substitution and rewrite this integral? Well, if I want it to be 1 over u, then u would need to be 12x minus 1. Okay? Now here's the thing. If you're going to do a substitution, you need to do it all the way. So this would be 1 over u, but the integral of 1 over u dx is not what we're trying to find. We want it to be consistent, and so we need to change dx to what it is in terms of du as well. So we're going to go, all right, if u is 12x minus 1, then du dx, or in other words, the derivative of u with respect to x would be just 12. Remember, just taking the derivative of 12x minus 1. So du is 12 dx, which would mean that dx is du over 12. And so when I go back up to my problem and start my substitution, rewriting everything that was in terms of x in terms of u, I would get 1 over u, the 12x minus 1, I just replaced it with u, times dx, which is du over 12. everybody okay right here?
Yes.
Okay. Now that would allow me to make this a 1/12, the integral of 1 over u du. Okay. All right, Timmy, it's going to be yours from now on. Whose derivative is 1 over u?
Natural log of the absolute value.
Yes, sir. So we have the natural log of the absolute value of u plus c. Or 1/12 the natural log of. Since this was an indefinite integral in terms of x, we want to make sure we leave our answer in terms of x. So I go back here, and where I have a u, I back substitute what u was in terms of x, and I would replace that with 12x minus 1 plus c. Now, that's one way to do this problem. It's not the way that I normally do the u-du part, but I think for a lot of people, this part is more comforting than what I typically do. Most of the time, just honestly, where I have this, I would say, I would stop here and go, okay, I have 1 over 12x minus 1 dx. And to get a du, I need a 12 dx in there. So I would multiply by 12. Already starting with the pens that don't work. I thought I had thrown them all away. So I would multiply by 12 and reverse it with a 1/12 out front. Then I could replace this whole thing with du, and I would have 1/12 the integral of 1 over u du. Now notice we end up the same place with those two methods. It's really just a matter of personal preference, whether you like to solve for dx and then factor out or multiply and reverse. I think I probably do it mostly this way because that's the first way I learned it, but either method is perfectly fine with me. Okay. All right. What about this guy? So we think kind of quickly through that list of 6 trig functions that we know how to integrate, and this is definitely not one of them. So we start thinking, okay, maybe I could do a substitution. How do we determine what to use for u? Well, in general, most of the time, the u will be whatever is being raised to a power in the denominator. Now, that's not always the case, but at least that's our first hope. So if I'm going with trying to make u be whatever function is being raised to a power in the denominator. If that's what I'm going to do, then my u would be cotangent x, because that's what's in the denominator and raised to a power. And it may just be raised to the first power. But notice that I did not include the power to which it was raised. I just took the cotangent x, because if I let u be cotangent to the 4th, then when I find the derivative, I'd be having to use the chain rule. And that gets messy in a big, big hurry. So we don't include the power to which that function is raised in our choice for u. All right, so if u is cotangent x, then du dx is the derivative of cotangent x, which is negative cosecant squared. So that means that du is negative cosecant squared x dx. You just move the dx over to the right hand side. And most of the time, guys, I will go straight from here to here. But remember, I'm just doing it today to emphasize that to find du, you're just taking a derivative. Okay. So rather than solving for dx this time, to get a du into my integral, I need a negative cosecant squared x dx. So I'm just going to multiply -1 and reverse it by multiplying by a negative out front as well. So overall, I've multiplied by -1 times -1, which is +1. So I haven't changed the value of my integrand. And so we would have negative the integral of this whole chunk right here is du. Cotangent is u, so I have du over u to the 4th. We have negative the integral of u to the -4 du. Now, before we integrate that, does anyone have a question about it so far? Oops. Okay. Integrate u to the -4. We will have the negative of integral of u to the -4 will be u to the -3 times the reciprocal of -3, which is -1/3, and then plus c. So we have 1/3, because we have negative, u to the -3 plus c, which is 1/3 times cotangent of x to the -3 plus c. Now here's where you have to be careful. For trig functions, you have to remember how it's okay to write the exponents. Cotangent of x all to the -3 could be written like this, or it could also be written like this, okay? The exponent can go completely outside the parentheses, or it can go between the trig function and the argument. What you can't do here is that is not the same as 1/3 cotangent of x to the -3, like that. This notation, x only is being raised to the -3 power. We want the cotangent to be raised to the -3. And then you look at the way they leave their answer in MyMathLab, and that's probably not it. Because when you have a trig function taken to a negative power, we could just write it as the reciprocal function. Which function is the reciprocal of cotangent? What's 1 over cotangent? I know y'all are there. Seriously? Come on.
Would it be cosecant?
Not quite. Which the other tangent? Tangent.
Yeah.
The reciprocal of cotangent is just tangent. So you could also write this as tangent cubed of x plus c. All three of these are equivalent correct answers. This one would not be the same thing. Okay. Remember, sine and cosecant are reciprocals, cosine and secant are reciprocals, and tangent and cotangent are reciprocals. All right, so what about these two? Well, I'm looking at these two. Okay. I mentioned earlier that when you're doing substitution, most of the time you take whatever overall quantity is being raised to a power in the denominator. Now, in the example that we just did up here, it was the entire cotangent being raised to the fourth power. So the denominator was something to the fourth power. When you have sums and differences in there, it doesn't usually work that way. In other words, you don't usually just take just this piece as the u value. If you had something like this whole thing raised to a power, then you might. But these two guys, even though they look fairly similar, you would not do the integration the same way. It's weird. But unless you have a natural log involved or a logarithm of some sort, which we do not, most of the time the u that you choose for substitution will come from the denominator. So our first hope is that we could just take whatever the denominator is. Since it's not being raised to a power other than the first, I'm just going to take the denominator and see if I can make that my u. If I try that in this case, then the derivative of u with respect to x is what? Well, the derivative of e to the 2x is e to the 2x times the derivative of 2x, which is 2, and then the derivative of the 4 is 0. So du would be 2e to the 2x dx. Does that make me happy? Well, in this case, yes, because to get my du, I needed an e to the 2x, a dx, and a multiple of 2. So I'm just going to multiply the numerator by 2 and reverse it with a 1/2 out front. Or if you prefer, you can do the dx is equal to du over 2e to the 2x and do the cancellation. But for me, this guy right here is my du, and this is my u. So I have 1/2 the integral of du over u, which is 1/2 the natural log of the absolute value of u plus c. Back substitute what that is in terms of the original variable, and we would have 1/2 the natural log of the absolute value of e to the 2x plus 4 plus c. Now, you enter that in MyMathLab, and it comes up and either says it's wrong, or you look at their answer and it's not the same thing, and they have this instead. And you go, well, but my teacher told me it was the natural log of the absolute value. And that's true. The difference is e to the 2x plus 4 is always positive, because e to a power is always going to be a positive number. And if you add 4 to that, you're just getting a bigger positive number. When what's inside the natural log absolute values is already positive, they'll oftentimes leave off the absolute value signs. So I just want you to be aware of why they're doing that. Are y'all still okay? Okay. Could we use the same substitution here that we used in this one? Well, if we try that substitution, I would need an e to the 2x in the top. The problem is I only have an e to the x, not an e to the 2x. So this substitution wouldn't necessarily work for that integral. And so we go, okay, well, maybe I can't just write this as a u to a power du. And so I have to start thinking about other integral forms that I could make work. So if just u to a power du won't work, what if we thought about this as this? Do you agree at least that those are the same thing?
Yes.
Good. Because remember, when you take a power to a power, you multiply the exponents. So e to the x all squared is e to the x times 2 as the power, so e to the 2x. So these guys are the same, and 4 is 2 squared. All right. So this, if I choose u to be just the e to the x, then du would be e to the x dx. And this would be du over u squared plus a squared. Or in other words, it's an arctangent integral. So the a is the constant that I have squared. And like I said, guys, we didn't do, at least in this textbook, a whole lot of these inverse trig integrals in section 5.5 or 4.9, but we will practice with them more going forward. So don't stress about them too much. All right, so we would have, in terms of writing it as an integral on my list of 18 things I know how to integrate, this part would be du. This is u squared plus a squared. So we have du over u squared plus a squared, which if you look at your formula sheet, we have that is 1 over a arc tangent of u over a plus c. And in this case, that would be 1/2 arc tangent of e to the x over 2 plus c. So particularly with exponentials and logarithms, it depends on how the powers match up. When you have powers matching for the exponentials in the top and the bottom, sometimes you can just use your straightforward take u from the denominator. When they don't match up, you're going to be looking most of the time at an inverse trig integral. And if there's a natural log involved in the integrand, most of the time that's going to be u, with the techniques that we know how to do right now, which is not much. We know how to do exact integral forms, and we know how to do u substitution, or just a basic substitution. And so with what we have at our disposal right now, if there's a natural log of x in your integrand, it's probably going to be what you choose for u. Okay. Now, moving on to definite integrals. Okay. When we do these indefinite integrals, in other words, we don't have any numbers at the top or bottom, remember the answers that we get are functions or classes of functions whose derivative equals the original integrand. But when you do definite integrals, remember you get a constant as your answer, and that constant is related back to the area between the graph and the x-axis. But let's just do one of these kind of and go through the definite integral part. Let me do a really quick one first. Okay, so what if we had the integral from 1 to 2 of x to the 5th plus 2x dx? Remember, for definite integrals, we're just going to ignore that for just a moment. We're going to do the indefinite integral part, which would be 1/6 x to the 6th plus x squared, and we're going to integrate that from 1 to 2. Now notice, after you've done the integration part, the integral sign and the dx are gone because we don't need those anymore. But before we do the substitution in here, we're going to have a vertical line with the top limit on top, bottom limit on bottom. This indicates we've done the integration part, but we still have to plug in the limits and subtract. So we plug in the top limit and subtract what we get when we plug in the bottom limit. Now remember, it's always plug in the top limit and subtract what you get when you plug in the bottom limit, never the reverse, because you'll always get the opposite sign when you do it in the opposite order. So we would have 2 to the 6th is what? 64? plus 4 minus 1/6 minus 1. Now, one thing you want to keep in mind on these, and for those of you that do have a graphing calculator, I would still expect to see this step, even if you're plugging it into your whatever kind of calculator. Now, once you get past this step, go ahead and plug it in and see what you end up with. That's fine. But be careful on your, in MyMathLab, because sometimes they'll ask you for exact answers, and I will almost always ask for exact answers so that I don't really want to see a decimal approximation most of the time. So we will have 64/6, which is 32/3, plus 4 minus 1/6 minus 1. So my common denominator would be 6. I should have left it. So what? 88 minus 7 is 81/6. Okay. So you've all seen this process before, right? I'm going to go with yes. Okay. All right. Now, we do the same thing when it's an integral that requires substitution, but it's kind of a personal preference as to when you deal with the limits. Okay, so for this integral, if I'm not even worried about the definite integration part, the first thing I would do is choose u to be the expression in the denominator that's being raised to a power. So I'm going to choose u to be x squared plus 1. So du will be 2x dx. Remember, to find du, you just take the derivative of u with respect to x and move the dx over to the other side. So this whole chunk right here is my du. So I have the integral of du over u squared. Now, we have a choice. We can either change our limits to u limits now and not back substitute later, or we can proceed as we are and then back substitute and plug in our x limits. That's what I'm going to do first because it's most similar to what we did over here. So if I leave my limits as x equals 1 and x equals 3, I must say we don't typically write x equals on those. I'm just doing it for emphasis that these are still x limits. I did not change them. All right, the integral of u to the -2 is u to the -1 times the reciprocal of -1, which is also -1. And that's from x equals 1 to x equals 3, where we have -1 over u from 1 to 3, which is -1 over x squared plus 1 from 1 to 3. Notice, I left my limits the way they started. So after I did the integration part, I had to back substitute what u was in terms of x, just like we did in our indefinite integrals. So at this point, I would plug in the upper limit and subtract what I get when I plug in the lower limit. Okay, oops, except I didn't plug it in there, did I? So I will have -1/10 plus 1/2. So that's -1 over 10 plus 5 over 10 is 4 over 10, or 2/5. Now, I do it that way sometimes, and your book does both of these methods. And so it's important for you to be able to follow and work with either method. Here, we left the limits as the original variable limits, and we back substituted in terms of the original variable. The other option is up here where you say u equals x squared plus 1 and du equals 2x dx. At that point, you can go ahead and change your limits to u limits. So we could say, okay, if x is equal to 3, that means that u is equal to 3 squared plus 1, which is 10. And if x is equal to 1, we would have u is equal to 1 squared plus 1, which is 2. So here we would have the integral from 2 to 10 of du over u squared. Now remember, for emphasis, this is a u limit now. I've already done that back substitution that I did down here earlier. I've already done it. If you do it originally and change your limits to u limits, you don't ever have to put an x in there again. So here I would integrate and get negative 1u to the negative 1 again from 2 to 10, which would be negative 1/10 minus a negative 1/2, or 4/5 again. It really is 6 of one, half a dozen of the other. It just depends on when you would rather plug those values into u. Here we do it first, here we did it last. But it is a valuable skill to be able to follow when someone does it either way. And your textbook, depending on, I think it does it both ways in various different places. Do you guys have a preference? Let's say this is option 1 and this is option 2. Do you guys have a preference on which one you do? I will try to remember to do some of both just to make you familiar with both. Oh, sorry, that's 2/5. So sorry. It was 4/10.
I usually prefer using the where you make x, well, x equals 3 to like u equal, well,
Change your limits.
yeah, number two.
That's fine. And I think, you know, once again, it just depends on probably a lot about how you learned it first. And, you know, some people find that this, I don't know, it's maybe a little, you're doing the exact same thing. I don't know. It just depends on when you do it. There are some situations when we do improper integrals, I like this method better, but I do this method a lot too. So yeah, I think it really is a personal preference type thing. Okay, any questions up to this point? All right. So what about this guy? Can anybody tell me what you think the integral form will be on this one? Of those 18 things that we know how to integrate, which one is this? Could I use just a u substitution with u equals the denominator? Well, if I tried that, my du would be what, 98x dx? And so I would need a 98x up there. The 98's no problem. I can multiply and reverse with a 98. But the x is a problem because if I multiply by x on the inside, I have to divide by x on the inside. You can never factor the variable of integration outside the integrand. And so that probably won't work because if I had to multiply by x here and reverse with an x here, then I've just moved my problem from the top to the bottom. I have an extra x now that I don't know what to do with. So probably not that.
Can't you use like arctan?
How about that? Exactly. This fits the formula for du over u squared plus a squared. Okay, and that is an arctangent integral. So you have to identify what is u and what is a. U is the variable expression that is being squared here, so that would be a 7x, and a would be the constant that's being squared there, so that's going to be an 8. We do just arbitrarily take the non-negative constant there just to make things simpler. And so du would be 7 dx. This is what people oftentimes forget to do when it's not just like x squared plus 4 or x squared plus 9, something like that. When the variable expression that's being squared is not just x, you do need to follow through your substitution or you will get the wrong constant out front. So I need a 7 dx, so I'm going to multiply by 7 and reverse it with a 1/7 out front. And then I will have 1/7 the integral of du over u squared plus a squared. And if we're going with, I think it was Avery that said they prefer from 0 to change the limits to u limits. So let's go with, okay, if x is 8/7, then u will be 7 times x, or 7 times 8/7, which is 8. If x is 0, u is 7 times x, so that's going to be 7 times 0, which is 0. So my new u limits will be from 0 to 8. And we will have 1/7 arctan, or tan inverse, whichever you prefer, of u over a will be 7x over 8 from 0 to 8. Oh, dadgummit, I changed my limits, didn't I? U over 8. Did I mention I usually do it the other way? Okay, since I changed my limits to u limits, I don't back substitute what u was in terms of x. All right, now plug in the top limit, and we'll get 1/7 the arctan of 8 over 8. Plug in the bottom limit, we'll get 1/7 the arctan of 0 over 8. So we have 1/7 the arctan, or tan inverse, of 1 minus 1/7 the arctan of 0. And the question is, what are those? Well, the arctangent of 1, remember, that's when you're finding an angle in the interval from -pi/2 to pi/2 whose tangent is 1. So the arctangent of 1 is, tangent's 1 when your reference angle is 45 degrees or pi/4. So this would be pi/4 minus the arctan of 0 is 0. So we end up with pi/28. Questions? Really? Okay. Well, I'm going to try to share the MyMathLab screen. We'll see how this goes, since, as I mentioned, everything's a little bit slow on sharing today. So let me pull this up and see if I can get there from here. Which may or may not happen. Well, that's promising. Okay. How many of you have used MyMathLab in some situation before? You can either raise your hand or you can just type yes or something like that in the chat. Okay, so are only like 3 or 4 of you still in here? You're still showing up. Okay, so let me get back. Sometimes when I use a pop-up, I have to get out and get back in. Okay. Okay. So do you guys see the assignment page?
Yes.
Excellent.
Yes,
Okay. So these guys, if you've used it before, I know you're familiar with these. I'm just going to click on section 5.5, and I'll probably have to get back out because this is a pop-up window and it blocks the pop-ups from sharing. So let me try that again. There we go. So this is a homework set in section 5.5. So you're just going to be integrating these problems. One thing I wanted to bring your attention to, but I also want to caution you. First of all, see that click the icon to view the table of general integration formulas. You won't have those on your quizzes or exams, so just be aware. That's why you need to memorize them. You also have question help over here that will help you solve this, view an example, view a video or textbook, that kind of thing. While those are excellent helps, I find that people oftentimes get too dependent on them and they miss them very much when the test or quiz comes around. So try to use those sparingly. I really like the Ask My Instructor one because that'll send me an example, or it'll send me a picture of your question. When you do that, if you'll just tell me where you get stuck on it, I'll do my best to help you navigate to the correct solution. Also, anytime you're stuck on a problem or you're getting it wrong or something like that, but you think you've got some idea of what's going on, if you will send me a picture via email of what you've done thus far, I can, see what your work was and see maybe where it went wrong or try to get you back on the right path. So that's usually a pretty helpful and quick way for us to get some collaboration done. You can, as I mentioned, we can have office hours anytime after this class. I'll typically stay in here or be available from 1:50 to 2:20 on Mondays and Wednesdays, or you can make an appointment through the link in Canvas. So what I'd like for you to do between now and Wednesday before class starts is complete the homework assignments for 4.9 and 5.5 in MyMathLab. I know it's going to take a little time to get, into MyMathLab today if you're not already and all that good stuff. But if you could work on that and get those 2 review sections assigned, we'll start actual Cal 2 new stuff on Wednesday. Okay. Does anybody have any questions? Would you at least, oh, go ahead.
I said no, ma'am.
Oh, okay. Sorry. But if you do have any questions, guys, I know that assistance and it's just everything's different, but know that I'm here and we will figure out a way for me to get help to you. Okay. You just have to be willing to, we just have to try different things sometimes. I think the Zoom office hours, I can make it when there's only 2 of us. It's not as big of a thing, or maybe 3 or 4, it just depends, but you can share your page so that I can see what you're working on if you want, or something like that. And it'll be more similar to just regular office hours. But let me know if you have any questions between now and Wednesday. And otherwise, I will see you Wednesday, and come prepared just like our normal classes. if you have homework questions, I'll give you a chance to ask homework questions at the beginning of class. And so we'll try it that way. It depends on how quick Zoom or how quick Canvas is. I may have to write those down. So if you want to send them to me ahead of time so that we don't have to waste the time, you know, going through the Canvas windows, that would be okay. But if not, it's okay as well. We'll try to get all your questions answered. All right, so if you have no questions, enjoy your extra 7 minutes of your day because it won't happen very often. And I will see you on Wednesday.
Professor Vaughn, I
Yes.
do have a question about the, I guess, inclusive access that was charged to our student account.
Yes.
Um,
If you have a code, like wasn't it you that had told me you already had a code?
Yeah, I bought one.
Okay. If you want to use that code, you can go into course materials on our Canvas page and choose to opt out, and that charge would be removed.
Okay. And if I choose to pay for the inclusive,
Then you would want to take your code back to wherever you bought it if you can.
okay. And then when I pay for the inclusive, do I automatically get into my lab math?
If you go back, let me see if I can pull it up here. Okay. I'm going to try to stop this share and hopefully go back to be able to share our Canvas class. That may be a bit of a stretch for me. Okay, I don't have it pulled up right now, so let's see. Don't want that. Here, there we go. Okay, I found it, so now I just need to share it again, I think. Maybe, okay. So can you guys see our Canvas course right now?
Yes.
Okay. So if you go to our home page on Canvas, which is slow today. All right, is the home page showing up for you guys now?
Yes.
Okay. Down at the bottom, in red down here, if you choose to use the inclusive access, that's the access code that you will use.
Okay.
And once you use that access code, they know that you will be paying the bill that you received through NWAC. If you don't want to, you can go back up here to course materials and opt out and then use whatever code you had. Because like if you had a code from the summer or spring that you still wanted to use and you chose to opt out, then they would remove that charge from your bill.
Okay. All right. Thank you.
You bet. Anything else? All right. Well, I will see you guys. Well, see, maybe a bit of a stretch, but I will talk to you guys on Wednesday then, if not before. But like I said, if you have any questions in the meantime, please don't hesitate to reach out and email me or make a Zoom office hour appointment and let me know, and I will do my best to help you.
Thank you, Professor Tracy.
You too. I'll see ya.
Talk to you later. Bye.
Bye.